Record. Okay. We are back. Good. Okay, so big thanks to Cristina and Shar, who are going to be leading this afternoon's talk and discussion. They've been leading the development of fast transient filters for Rubin, and so it's a sort of a good transition from images to photometry. And so, yeah, I think you should both take it away.
Okay, so like Michael said, Shar and I have been working together to develop transient metric filters for the Rubin Observatory, and we're evaluating using manufactured light curves to determine which proposed cadence for the legacy survey of space and time is going to be the most efficient for detecting these fast transients. And so we're developing different science cases, so LF-bots, GRB afterglows, kilonova, shock pooling emissions, supernova, and a few others, and dwarf flares as well. And so in this notebook, you'll be guided through a demonstration of the process of evaluating how well an astronomical survey cadence will detect rapidly evolving transient phenomena. And we're going to be using kilonova as an example. And so the Rubin Observatory will carry out a 10-year optical survey of the sky called the Legacy Survey of Space and Time. But how the sky is observed, when, where, and in which filters is not fixed currently. Rubin's team, the Survey Cadence Optimization Committee, designs and tests different strategies to maximize scientific return across a wide range of priorities. So supernova, asteroids, gravitational wave counterparts, and many more. And one of these cadences will then execute the Legacy Survey of Space and Time.
That's right.
Okay. Each cadence is simulated 10-year observing plan that specifies how frequently each patch of the sky is revisited, which filters are used in each visit, UDRIZY, and the depth and timing of these observations. And so we have baseline, rolling, they have different characteristics, and Shar will then be going over that.
All right. So while I talk about that, everyone make sure you can open this notebook, make your own copy, and start to install stuff. So
you can run the first two cells if you're on Colab, or if you're in the notebook, run these two cells here.
Yeah, and if you're on Colab, that's when you should make sure you make your own copy so that it'll save your changes. So yeah, like Cristina mentioned, you know, in astronomy, we used to just everyone looks at their favorite object in the sky, and we don't do that anymore. I mean, some people do that, but we are in a new era of astronomy where we have our telescopes carrying out these automated sky surveys like ZTF, like Rubin, and that means that you need to make all the decisions about where it's going to look ahead of time, instead of just being like, oh, I heard there's something cool over here tonight, let's look there. And so, yes, the Rubin Observatory has been under development for very many years now. And I'm not going to go over every single one of these different considerations for the cadence, but regardless to say, there are many of them, and you guys are not going to look at all of them today. But certainly we're going to see how often each part of the sky is revisited and what that means for finding fast transients, where we're using a kilonova as an example of a fast transient. Fast means just it evolves more rapidly than your typical supernova that you would use for cosmology. Did anyone have any issues installing or importing stuff?
And if you are running into some errors, you can pip install these libraries as well.
Yeah, there's two of us, so I can run around the room and answer questions, and as well as answer questions on Slack. And then just so you all know, our notebook is split up into 8 sections. So we're gonna give a little spiel and then give you a few minutes to work on a section and then come back together and move through it just like that.
Yeah, this is a really well organized notebook, and so you'll have the introductory information. We'll give you something to work with, some code, some structure, and then for you guys to fill in. And then afterwards, there under solution is the solution for you guys to look at in case you need some help, some guides. Afterwards, we'll have an explanation and then a discussion section, so you guys can ask yourselves questions or kind of evaluate your understanding of what's going on.
Mhm.
And so this new notebook will be using, like Shar said, a simplified version of these cadences to test how different observing strategies will affect our ability to detect past transients. And we'll understand how Rubin surveys the sky is key in designing metrics. And so if you want to know more about how Rubin functions and how, the essence of how we designed this mock cadence, you can read into what our survey cadence is during the next break. But if there are no questions at this moment or no, hey, this isn't working, I can move on to the next section.
So did you create a brand new brand? You said, so I put it in the data model.
Do you have any issues with heel pie and SciPi being enemies?
We didn't. It doesn't mean that you won't.
At one point,
Yeah,
there was issues with this.
okay.
There is a way to pause SciPi. So he,
I wonder, you could maybe print the versions, like, make another cell and then print the version of SciPi and HealPi to allow them to
Sure.
install specific ones, if you just, like when you're in collab now. So if you go, yeah, like make a new cell and print out SciPi dot underscore version. Yeah, it should be SciPi period
SciPi period version.
underscore, well, maybe it's version. I think you can always do SciPi on dot underscore version. Maybe it's not.
I think you just type.
Did you run the first cell? Like, did you rerun your?
Yeah, I did a few minutes ago. I did clear the output, so I could have done the same thing, yeah.
SciPi.
Do we need access to dust maps directory?
You have to install dust maps, so it's in that first install section. If it doesn't work at all for you, then we can
import SciPi.
Okay, yeah.
Word permission denied that access.
Okay, and then also.
I also have 1.15.
Okay, and then now HealPi, what is yours?
I installed HealPi fine, but HealPi is importing something from SciPi as broken.
Below.
Yeah. Let's see what.
Maybe you need to restart.
Alright, can you launch your version?
No, because I can't import HealPi.
Did you say
That's
dust?
for Rails,
yeah, that's.
I see, so, but you can,
but it is
but you
installed.
can pip install.
I didn't run that, I'm just installing it in, so.
Okay, so
This-
can we check your version? You should, can we try pip installing?
Is that gonna break that it's already installed in Anaconda?
Yeah.
Okay.
You can conda install as well.
I did,
Shorting buttons.
I did install the 5 and Forge, and it does,
Fine,
and it installs.
which you end up with 1.16.6, so I think we want to do this. So let's try pip install. You do like pip install double dash upgrade. Cool. See if it'll.
And that's 1.16.6 still, if this is that too.
This is,
If it's
yeah.
not.
this is the.
Yeah, go back to your.
Yeah, I found the upgraded
That may be working.
Yeah, I'm just so.
I made it fix.
Yeah.
Darn, figure it out.
Okay. Skylar's trying to.
She was still on search.
Stupid.
I can use Daniel's technique.
Yeah, I made it past that, I never did.
Okay, unrelated.
Yes,
Well,
unrelated problem.
Okay. You're ready.
Skylar, you said?
Yeah, as far as you're concerned.
Oh.
When in doubt, look again.
And reminder to folks, you can reach out on Slack if you have
Yeah.
installation issues. We can try to debug over Slack.
Yep. So cadence refers to how and when a telescope revisits the same area of the sky over time and which filters. So spacing between observations, the depth of each exposure, and balance across filters. And this really controls what Rubin will be seeing. And so for the first section, we're going to generate a simplified Rubin-like cadence using randomized observation times across a heel-pix grid of the southern hemisphere. This will set the foundation of the entire filtering pipeline. It'll determine when and where the sky is observed, which limits when transient events can be detected. And so this cadence will affect revisit times, temporal gaps, so how much space is between each visit, revisit, and in which filter they will be covered. And so in part A, we're going to generate a Rubin-like mock cadence over the southern sky. And so I want you to run the part A cell. And so this cell generates a baseline cadence over the southern sky, which you'll be asked to replicate and extend parts of this logic in the next section. And so we're simulating the southern sky coverage, and so we're limiting it to, less than 10 degrees, so the southern sky. We can have theta or TH and pH, so we also plot across a sphere, putting into degrees, and then we're masking the sky, so sky mask. That's the southern sky, so 10 degrees down. All right, then we're going to set up the survey. So how long is the survey going to go on for? 10 years. We have how many filters? 6 photometric filters. Is everybody getting a cell, a plot?
If you're not, look confused.
So raise your hand and say, yo.
I got that. I have a different problem.
Okay.
That's rude.
Is it, so dust maps requires a download.
Yeah. It's quite nice.
It's so small. You'll find there's no actually.
But this is itself. Is your line laptop?
Yes.
If you open or you can sell and just do like HDDOC version.
What's up, pal?
Oh, I installed it, I didn't import it.
Yeah.
It
Because you have to-
installs FieldPy, but it won't import it.
What do you mean? You have to put import HealPy as HP. It should be up here, so you just rerun this cell.
Can you just try to run
Yeah.
these couple of months ago?
Sure.
Just to.
Your shit will.
There, yeah,
Yeah.
there.
Suspect.
Tim per day, day,
Thank you. I'll get it.
I don't know. I have admin privileges also, so I should be able to download stuff. This account doesn't, but I do have like an admin.
It failed to build the wheel for FieldPy.
So, I have to-
Uh-oh.
Okay, but you're on your Windows. Okay, this might be a collab
Okay,
thing then. We might need to.
Including
What's up?
suggested things.
I'm running Windows and this probably.
Sorry, Sarah.
Okay, so is this?
Yeah.
So yeah, so let's go grab this line.
Okay, so you might have to do it on Colab.
Okay.
Yeah, let's open up.
If you're on Windows and you're getting a Windows does not support error, then you need to run it on Colab.
Yeah.
Okay.
You're getting it? Good.
On your Windows.
Does it look like that?
Yeah, something like that, yes.
It's exactly like that.
I'm gonna
Perfect.
put this.
Then it's working.
I'm thinking these two lines.
Definitely does.
Yeah, because so one, we should change the content. Probably put this data dirt somewhere that you can actually write to. And then. Yeah, because so this is appropriate for collab, but for you should put it.
I think that's.
I think it's safe to go on.
Let's
Sorry.
wait another minute.
Is anybody else running into issues?
If dust doesn't work, that doesn't really matter. We can
Okay.
pretend there's no dust in your galaxy.
That would be, that might be the best.
Easiest way to be the moon.
Perfect solution. Better car science.
Yeah, no.
That's amazing.
Like, it's there.
Well, we'll try.
Water, no air, maybe it's rapid.
Oh,
Just since where I went to college, there's a gravitational one, so all of our stuff is a little. 9.81 isn't a good gravity.
what's the time down to?
There's a lot of metals here. The UP. The handboard places on Earth, we can just dig out.
Okay, so give me try commenting out that, hopefully if you comment out those dust map lines, we'll just move on then. It's all good.
Right, that's what. More calls from Cristina, says. I'll do one on call out.
So I think it's,
There we go, all right, thank you, yeah.
are you, how are you running yours? Do you have some content environment or something?
I made a content environment
Yeah.
and I did like pip install a heal by then.
I know what you're talking about. What are you doing?
She tried to do the same routine on this and it wouldn't install the wheeler.
But at the same time, I don't think this is a content environment.
Yeah, it's straight
Like,
Python,
it's a
right?
content environment, it's like a. I don't know.
Yeah.
different one.
Let's just do it in Colab, pal. I think that's easier.
Okay. Everybody static or know what's the next thing you do? So how do we do this? How to create this, funky blue fuzzball here? So we have to define a sky resolution, 64, pretty standard. We're gonna limit it to the southern skies, less than 10 degrees declination. All right, and then we have the survey set up. So we're gonna initialize, how many years are we doing this for? 10 years. And what filters? We're gonna label the filters, create an array here, UGRIZY. And then this is just a approximate Rubin visit library.
Can you make the screen a little larger, please? That helps. Thank you.
Perfect. All right, so here, we're just going to quickly define the visits in general for each filter. We're gonna initialize the mock cadence. We're basically just, initializing our library, what's gonna look like our pickle file. All right, we're setting a random seed. We're gonna create a container for the pixel indices, and then we're gonna iterate. So every year, starting at this MJD, which is sometime in the fall of 2025, and then we're going to do this for 10 years, adding 365.25 each time. So that's about a year. And this is just stuff to organize the MJD times, the total visit map and all filters, and then we plot it. We're using a mul view plot because it's not a Cartesian plot. And then we save the pickle file. And so here we're seeing generally how the visit's gonna look like over a 10-year survey. So in all filters. And so you can see the range of visits here. I'm gonna save this mock cadence into a pickle file. Now, when I'm running these locally on my computer and I have the whole metric analysis framework for Rubin, it's a DB file, and it's very large. This is relatively small. All right, and it just goes to show the extensiveness of Rubin and what it's capable of, that it takes what are these DB files, like 3 gigabytes? And so here, the next step is going to be a challenge for you guys. We're going to be simulating a 5 sigma depth variability for the R band for year 3. And so Rubin's cadence is not uniform across all filters or years. Some regions will be getting more R band visits, some will be getting more I band coverage. Different years also see different cadences. The depth of a given observation, meaning the faintest detectable magnitude for that observation, varies due to sky brightness, the seeing, the air mass, and the weather. So Rubin's expected depth per visit are about 24.7 mag in G and R, I and Z is 24 to 24.5 mag, and Y is about 23.3. And so this 5 sigma depth that I've mentioned is the faintest magnitude that Rubin can detect with high confidence in a single visit. And so how faint can it see, all right, with the best confidence, so it says, I am sure I'm seeing this, all right, when it just takes one image in a single visit. And this depth isn't constant, it depends on observing conditions, like I mentioned before, the sky brightness, the air mass seeing. And so in some places in years, Rubin will be reaching much farther, much deeper and detect fainter objects, and other times there won't be. And so the point is that which cadence is the most efficient at capturing fast transients with the best confidence. And so the following exercise is going to help visualize that variability by simulating it for a specific filter. And so use the dictionary that we just built for the mock cadence to simulate the 5 sigma depth variability for the R band in year 3. So you're going to extract observation times in the R band for the correct year. You're going to count how many R band visits each pixel received in year 3. For each pixel, you're going to simulate a 5 sigma limiting depth using Gaussian, and then save the median depth for each pixel to a HelioPix map, and then you're going to plot it. And so I've created a infrastructure, kind of a shell for you guys to fill in, and then if you guys get stuck, you're not sure what to do next, you can use the solution to kind of guide you through it. And then Shar and I will be here to answer your questions as well.
Both coding questions and like theoretical, like what's a telescope? We can use.
It's good.
This is maybe answer that. Maybe, okay.
AJ, do you need any help or anything? We're good. And so for, let's say that first line of the year index, this is gonna be, you know, Python indexing, so what is the third year, 0, 1, 2, it's gonna be 2. And so the next step is creating an empty HelioPix map, so we're kind of saying, hey, this is what it's gonna look like, and then we're gonna fill it in. Here's a little bit of a hint for you to see what those first few lines look like. And so we're going to be adding through the year index. Right, and then +1, so we're gonna do up to that point. Let's do pluses. So let's move on to the next section. So this is what you're supposed to have done. So you're going to, so for pixels times throughout the mock MJDs for the filter R, you're going to iterate, all right, between year 0 and year 3, or year 0, year 2, for the number of visits, the length of times in year. And then if the number of visits is greater than 0, so that means that if like Rubin actually visited that space, it's going to count, it's going to simulate the depths, all right, and then it's going to test the average, and you're gonna plot it. And so depending on what model view you have set up, or depending on if you have a specific like C map, like vertex is a specific color mapping for it, you're going to see a variety of colors here. What you're really looking for is the range of depths, 23.5 to 26. Mine sits right in the middle, that's fine. And then, so the next section, so this is like actually 1 point, this is like 1B. On section 2. All right, now what we're gonna do is Right, you wanna do explanation? Or you want me to do it?
Yeah,
I'll
the
go
first
on.
one.
Yeah, I'll talk about the equipment thing.
Well, I was gonna ask the discussion questions and see what people thought. So if you've managed to plot both the full 10-year survey and just 1 year of the survey, did you notice any differences? If you haven't done that, what kind of differences do you imagine there might be?
Remember, we're visualizing how depth timing varies for each iteration of the cadence over 10 years. So what aspects of this do you think will change between year 1 and year 3?
Do you think that you will see the same number of visits in year 3 compared to all 10 years?
Do you think the density will increase? Will this number increase or decrease? And so magnitude get better or worse?
Can you show the plot again?
Yes.
So, would you expect it to be more blue or more yellow?
They just thought focus. So,
Alright, well, you can type your answer into the discussion question. You're getting nothing, alright,
just
so
getting the blank.
I'll come
least
look
it's
at that.
running without errors.
It is, at least it's running, okay, so, you should see something like this when ultimately you do get this to work. There are less visits in year 3 compared to all 10 years, as you will have guessed. So one question that comes up often is, how uniform is the Rubin Observatory's survey cadence? So just like, there isn't really a right answer to this, but looking at your plots, would you say like this cadence is uniform, isn't uniform?
A little bit harder to tell with this one. If you look back, you can see, over 10 years. And so
Simulated 10-year visit count.
More blue.
There's more granularity in the top one.
Yeah. So like all things, the answer is like, to a degree, it is uniform, but there certainly are places on the sky where you're getting more observations, especially over all 10 years when you stack it up. And yeah, we have some good comments.
yeah, more visits equals higher chance to look deep equals more yellow.
Yeah.
That's correct.
So now we are gonna take this very basic map of the cadence and we're gonna make it a little more accurate.
Yes, because we do exist in a galaxy. We don't exist in a simulation. So overall, a simplified cadence map lets us test how different areas of the sky are sampled over time. By visualizing the number of observations per pixel, all right, especially in different filters and in different years, we can see how Rubin is going to be building on the previous images to really get that depth, that understanding of the cosmos. And so the simulation shows us that cadence isn't just about when we observe, it's about how well we observe the quality of each visit over time. And so by mapping depth across the sky, we can start to identify regions and time periods where detection is much more likely, specifically for science cases like kilonova. And so now what we're going to do is we're going to be masking out areas like the galactic plane, the ecliptic plane, and we're going to be like filtering out those really, really low visit areas. And so what is the ecliptic plane? So the ecliptic plane is the path the sun traces through the sky over the course of a year, closely aligned with the orbital plane of the Earth and major planets. And so this is going to get rid of a lot of noise in our photometry. And so this region centered on the ecliptic latitude, 0 degrees, is often crowded with like solar system objects and things that just get in the way. And so good for other science, not good for us. And so cutting at this removes the plus or minus 10-degree band around the ecliptic. And so this helps us exclude areas with high contamination from moving objects in bright sky background, because kilonova are very faint, very fast fading events. And so it's a common practice for extragalactic or transient searches to avoid spurious detections or photometric noise in the ecliptic zone. So we remove it. And then we're going to remove the galactic plane. So the galactic plane is the dense, flattened disk of the Milky Way galaxy. So, you know, when you're at a concert, you have all this smoke coming from these rock and roll guys, and that's great. But then you can't see what's going on with the drummer in the back. So the kind of same principle applies here in science. And so cutting at 15 degrees excludes the central 15-degree strip around the Milky Way midplane. This removes regions with high stellar density and extinction, which obscure faint extragalactic optical transients. And so the cut improves detection efficiency and reduces confusion, which just wastes time and resources. And so for section 2, we're going to be constraining the space and masking this part of the sky. We're going to apply a field pick space galactic latitude mask and show how it reshapes our survey coverage. This uses the visit map from section 1, which contains a total number of visits per pixel. And so I want you guys to run this cell. And this is an example. I've done the first one for you, which is the galactic plane mask. I'm just going to show you how this works. So we removed the Milky Way. We don't like it. And so now we have a lot less contamination. We can be very specific with the area that we. What's up, Hal? It's perfect. Oh, great. So some cells aren't participating. Nice. And so this is what this looks like. And again, we're not working with Cartesian, we're working with a sphere. That's why we have these, you know, heel picks and HP dot picks to Ang, which doesn't like participating with SciPy. And now what this is doing is saying, hey, we're not going to be able to capture fast transient in this area. Let's just reduce it completely and really focus our resources on testing which cadence is going to be better for kilonova. And so you can see the variation in visits. So part A context kind of goes back to summarize what I just said. If we do the discussion.
No, I think everyone wants to code.
Okay, so now you guys got a challenge. So now what we're gonna do is we're gonna modify the galactic plane mask to instead exclude the ecliptic plane. We're also gonna do pixels with very low visit counts, so fewer than 50 total visits over 10 years. And so this exercise will explore masking strategies for avoiding solar system objects and to simulate the LSST's sparse edge survey regions, so the low coverage areas. So the first part of this code is we're using the RA and DEC from a visit map from section 1. We're going to use sky coordinates, so make sure we're plotting across an accurate sky. And then we're going to mask the ecliptic plane. And so very similar to what we did before, I want you guys to see how you do it.
We have to do both 1 and 2 in the final number.
Say that again?
So like we want mask both the ecliptic plane less than 10
So the
degrees.
first one, you're just going to be doing, I want you guys to see each one individually. So the first one was masking the galactic plane at 15 degrees. This cell right here is just doing the ecliptic plane, and the one below it is removing the 50 less than 50 visits.
Oh,
I have some. Yeah.
that is big. This is, solution.
The galactic and ecliptic planes removes regions where transient detection is unreliable due to crowding and moving objects. And this step makes downstream efficiency estimates more realistic and avoids overestimation.
Yeah, people online have already given some good answers for this, but so everyone else gets the chance what's a time when you wouldn't want to mask out the ecliptic or the galactic plane? What kind of object might you be looking for?
Say that again.
What's a time when you wouldn't want to mask out the ecliptic or the galactic plane? What's something you might be looking for that would mean you wouldn't want to get rid of those regions of the sky?
Okay, those big variables.
Cataclysmic variables, very true.
The general idea is that, and if you're looking for something within the galaxy, you're not going to remove the galaxy.
Yep, or if you're looking for anything in the solar system, you wouldn't want to remove that region as well, so. If you're looking for planet X, then definitely don't block out the ecliptic. Uh-huh.
All right, now we're gonna get to the fun part. All right, which is the most technical. So I didn't have to create a cadence. My first time creating a cadence was writing this demo. I have had to do a monumentous amount of light curve studies or light curve generative functions. So that means you're taking as many aspects, as many variables of an object's light curve and then programming it. And so
For the non-astronomers in a room, a light curve is basically a time series where you're like, how bright is this object the first time you see it? How bright is it the second time you see it? All of them. They're usually like irregularly sampled, which makes data science on them really fun. And hopefully everyone can, you can see through my Zoom because Cristina is in the galaxy, this beautiful drawing of a light curve being brightness versus time in days. Please continue.
And so it's the visible evolution of an object. For most cases, you're gonna start in the U, and then you're gonna fade into the red and the infrared. And so the 6 photometric filters that Rubin uses, U, G, R, I, Z, and Y, are the visible near and near infrared light. And so now we want to understand if we want to create or manufacture these events in space, because what we're doing here is that the first step was creating the cadence. So we're creating Rubin itself, we're creating the telescope and how it looks at the sky. That was your first step. All right. Your second step was now creating a more realistic space, the universe. So you're removing the galactic plane. You're going to reduce the number of visits to those dense areas of gas and dust. All right. You're going to cut off the sun so that we can make sure we're seeing clearly. So not only are you making it easier for Rubin to view, but we're also kind of creating the environment we're going to be looking into. And so we're both man and God when we're doing this. So the next step, which is now step 3, is that we have to now put these events into space or into our hypothetical space, all right? So we have to understand how it evolves in these 6 photometric filters that Rubin is using. And so this section is going to be creating these light curves or creating the events, the kilonova themselves, based on key physical parameters. So for the non-astronomers, when kilonova are actually 2 neutron stars colliding. And when that happens, depending on the angle of contact, you'll have ejecta coming at you at different angles. And so kilonova are optical and near infrared transients produced by the merger of 2 compact objects, typically neutron stars. These mergers eject material at high velocities and synthesize heavy elements like gold and platinum through our process nucleosynthesis. Basically, very fancy nuclear fusion. And this powers a rapidly evolving light curve. And so supernova evolve in weeks to months. We have sometimes less than a week, few hours, day maybe, for kilonova.
And that means that we haven't found very many of them in our history as astronomers. So we want to find more.
Yes. So in this model, we represent kilonova using 2 dominant ejecta components. And so when these objects collide, they're going to eject material. And so we have the dynamical ejecta, which is launched within milliseconds of the merger due to tidal forces and shock heating, so things being ripped apart and all this friction occurring. It's often asymmetric, fast, and very neutron rich, a lot of neutron particles. And this leads to a rudder emission. And then you have the wind ejecta, and this arises from post-merger remnants outflows, including neutrino-driven winds and disk winds. Very fancy way to say there's stuff coming off of it during and after the collision. Wind ejecta is slower, more isotropic, and can contain higher electron fractions, producing bluer emissions. And so here we're kind of seeing how these light curves are starting to be affected by the progenitor, by what's actually occurring in space. And so the observed light curve depends heavily on orientation. So we have our opening angle phi defines the angular spread of the ejecta, and our viewing angle theta specifies the observer's line of sight relative to the polar axis. So what happened, where did the merger occur, and are we seeing it directly, are we seeing it partially in 3D space? So a viewer near the polar axis may see a brighter bluer transient due to lower opacity wind ejecta, while equatorial lines of sight appear through the dynamical ejecta, so dimming and reddening the emission. All right, so I want you guys to, I pulled some values from M. Bulla's models, and give them to you. And these are going to be then fed into later down the line when we start to generate the light curves themselves. And there's going to be a little bit of theory here. There are going to be a few equations that you guys have to program and write into, but they're equations, and it really is just solving a word problem now. So easy, hard, depends on who you're asking. So go ahead and run the cell. And so if everything's running right, you should see like a total combination number. And so this is a variety of combinations produced by these minimum and maximums with increment levels. And so your first challenge activity is to make a light curve, is to match a light curve to the parameters. So we use a very simplified model where the absolute magnitude is adjusted based on the ejecta masses and the geometry of the viewer. We have a brightness offset that's a function of the magnitude, and this reflects the intuition that large ejecta masses produce more radioactive heating, brighter transients. And this also reflects the intuition that edge-on viewing angles reduce the observed brightness and lowers the optical depth.
So that's like,
Sorry.
is it coming straight towards you or is it going like a little bit up?
Yeah, which will, if it's coming right at you, you're getting all that light directly in your face. But if it's slightly off, then you're not getting all of the light. So the peak mag is the sum of the absolute peak magnitude and the brightness offset. And so here, now we're getting into the equations for those of us who are mathematicians, maybe your domain. And so these components offer a very simplified, parentized view of how brightness evolves with time in each filter. So a kilonova's light curve parameters is shaped by its ejecta mass, its geometry, its line of sight. And these parameters will affect how we see it evolve. So the rise in fade rates in magnitude per day, the peak absolute magnitude, and the duration of that peak phase. And these distinctions capture how the kilonova is dependent, how we view the kilonova is dependent on the wavelength. And so early blue emissions, U and G bands fade quickly, the redder bands persist longer, but they're fainter. And so this design is based loosely on our single event that we've observed in its entirety. And your task is to implement a function that builds a kilonova light curve using these simplified assumptions. And so I have given you a scaffold of the generative kilonova light curve function. I'm telling you what goes in, I'm telling you what it returns, and then your job is to follow the to-dos and fill it in. And so I've done the little array for you of the different rise and fade rates in each filter for the kilonova. You're going to compute the brightness offset, which I've given you the equation for. You're going to do distance modulus, the peak magnitude. Then you're going to construct the light curve and defining rise, plateau, or the rise, flat, and fade phases that are also given equations. And then how do they play together? And so this isn't going to return anything, this is just to build a function. And for those of us who may not be so familiar with coding at this level, is that we're just, this function or a function is saying, hey, whenever you call this, it's going to do this task, and we're just writing down the list of tasks that we want this to do, which is generate a like curve. The next cell is to then create a template or a series of these, which you'll just run automatically, but it won't work if your like curve function isn't complete. And so when we're generating the like curves, are we going to use the absolute magnitude or the apparent?
I would say the parent.
No, because we're generating the events themselves in space. We're not going to be applying how we see them yet. So we're generating the like curves, we're generating the objects themselves. So we're gonna do an absolute magnitude. Do you guys complete the writing the kilonova like curve function? So a good way to kind of start testing whether it works is to then run the template library function, which is a cell right below it. And that's already complete, you don't have to do anything to it. So once that's run, then you're gonna then run the cell below it that actually calls that function. So you're making sure that these two functions are then saved to this notebook. It knows what it is, and then you're gonna call the function, which is this right here. And so part two of this is that you created your like curves, you've now saved the templates. And so you haven't generated a population of events. All you've done is generated a series of like curves. They're not assigned distance, they're not anywhere really in space yet. We've created a series of like curves. And so now what we're gonna do is we're gonna see how the given parameters, so the wind ejecta, the dynamic ejecta, how the like curve parameters, how they function together and how they affect each other. And we're gonna run the cell to plot that. So we're gonna load the pre-computed light curve templates. We're gonna select a few individual examples. We're gonna plot the light curves in different filters, and we're gonna observe how the peak brightness, timescale, and color evolution differ. And so once you get through running the template, calling the template function, and running the light curve plotting cell, you should end up getting something that looks like this. And so if your template function ran correctly, you're going to see this output. And this is telling you that it generated 81 combinations. So you have 81 templates that now we can assign to anywhere in space when we generate a population, not yet. So here we're just going to be evaluating our light curves. So it should look something like this. Did everybody get this, or are we still having trouble?
And I should let them go for the function. Once they have.
And so this synthetic light curve for kilonova reflects realistic timescales. So a rapid rise, a slower decline, we have multi-filter variation, so they peak slightly different times. And so this activity mirrors the interpretation step that astronomers use when they model. And this helps to make sure that when we do our selection metrics, like what it takes to detect, what it takes to characterize these, we know with confidence that what we're plotting, what we're putting out into the universe, and what we detect is an accurate representation of the efficiency of an instrument. What is this session?
Yeah, I'm gonna put this in chat while people are still typing. Or if they don't type it, we can discuss.
What's your discussion?
As soon as you have plots that you're happy with, we have, right, if you wanna like get a sneak peek of the next sections, they're all there, but yeah. No, that's fantastic. Alright, so if you've managed to get a plot of your kilonova light curves, can you tell from these plots, whether your kilonova is evolving faster in like redder wavelengths of light or bluer wavelengths of light? And for the non-astronomers in the room, U is ultraviolet, G is visible light, R is red light, I is infrared, and Z and Y are that direction. That direction. Screen doesn't. Screen doesn't. Jake's light curves all look the same. Unfortunately, you do have a
They-
line somewhere.
They do look very similar, like the three that you picked out, which I did, and then was like, is that correct? But they.
Well, they are gonna look
they're
similar,
very
but all of
close to
these,
each other.
Look at the displacement though, in different filters of the same, technically, this is the same light curves, one light curve on here, but it's in different filters.
No, I mean, between your three different
Oh.
plots, they all look very similar.
oh yeah, Jake, if you're saying that the three different plots look pretty similar, you can check out where the black line ends. I believe it's slightly different.
Yeah, but not by much. You can change the indices between 0 and 81 if you want.
It's the same, actually.
It looks very similar.
That would be a bad day.
Actually,
Jake
maybe
is-
mine also look the same.
Jake's pointing out that maybe they are all the same, and so maybe there's a little bug here.
Yeah, I was like,
Probably
they look
a lot.
suspiciously similar to the point
Yeah.
that I'm worried.
You're so right.
You are very right.
But then I was like, but yours also looks suspiciously similar.
Something
Maybe it's
suspicious
fine.
is going on here.
Something questionable. I mean, I'll take the break to figure that out.
Yeah, so wait, someone tell me whether this single light curve we've generated is getting fainter
It
in
evolves-
bluer or redder filters.
It evolves faster and bluer.
Yeah,
Yeah, right.
And how did you come to that deduction?
The slope is greater. Yeah,
perfect.
and the-
All right. So keep in mind this that you've noticed the slope of
More.
all of these transients, because that is going to be extremely relevant when we come back from the coffee break. Please enjoy some coffee. Let us know if you have any questions, and we'll reconvene at 3:30.
Oh,
Yep,
Mega Wordle.
This is Mega World.
with the fixed
It's adorable.
notebook.
It's 16 words. Wordle. There's different versions of it.
We'll convene at 3:45.
3:45.
Yeah.
3:45, you get a long coffee break because they're nice to you here.
I don't know.
My brother actually got me the Mega Wordle.
Mega World is. I'm a connection to the.
Exactly. I used to live there at the time.
All right, it's 3:45. We've posted our bug fix on Slack and it's on GitHub. Now you are choosing from a range of parameters for your rise rates and fade rates and time at peak instead of every light curve being exactly the same. So Good job, Christina, fast coding.
So, just to kind of go over the changes I made, there's 4 of them in Slack. So first, I want you guys to change, I'm gonna copy, oh, I don't think I added it actually. By accident. Not here, I added it here, didn't add it to the Slack. Right here, okay. So that you can change the information. So where it says like challenge 1. Here's the corrected table, so it has the ranges in it, so you can see it formatted. You can put that right into the markdown.
We lost you.
Oh, it's okay. If you check on Slack, you can see it. So basically I sent this right here into Slack, so it looks formatted like this. And so instead of having like a single parameter here, we have a range of parameters that we're then going to we're going to uniformly distribute. And then the scaffold for you guys to fill out was also amended. Basically, I just added the new LC params dictionary, as well as the seed. If loop. And reformatted this to do a uniform distribution. That's also in Slack, you guys can just copy the scaffold. And then below the scaffold is the solution that you guys can also just copy in, there you can run it. No changes were made to the template generator. You can run those at will. And the last changes I made were to the lead curve plot. That's just going to iterate to a slightly different way. And let me know when you guys are about done with that, fixing all that, and then I can move on to the next section.
Yes, it was there 2 years ago, but my group generally gets it.
I have to get some.
I don't see anything on Slack. I've been trying to figure out where you put it on Slack. I have nothing there.
It's in the school 25 channel. Are you in that one?
I'm in ZTF 25-A1.
Okay, so that's not the one it's in,
It's in school 25.
25 is a private channel, you have to be invited to.
well, you all should have been invited to it. It's,
You just add whoever's missing.
We also all have privileges to add people. I have
Yeah.
that, because I added
That's,
other
you
versions
should
of myself.
add whoever Ivona is.
School 25, doesn't even come up on my screen.
okay, I'm gonna put here to tell me if you're not in the school channel. School 25.
Yeah.
And I'll add you.
I see 21, 22, 23, 24.
I think ideally we should also,
Does anyone make it public?
You asked me a question?
No, Michael.
I don't know, I think that's probably Ivona thing. So,
I can copy, I didn't know that there was that, so my bad.
yeah, maybe she has to take it. Okay. Okay, Jake. Oh,
Oh, why didn't I do that? Oh, it's like right here. Oh. But yeah, that's what I thought to do too.
I can also forward Michael, do you want us to do it in day one instead?
I think generally putting things in day one is good. I think school 25 is gonna,
Okay.
for general announcements and, I don't know, Ivana made it, so. Actually.
Okay, why don't you keep talking and then people can, I'll do the slide thing.
Mhm. Alright, so. I'm gonna show you guys what the completed light curves look like. And so now we have these, they look like this. Alright, so we're looking at template 1 and template 80. Now there is something a little weird going on here with some of these. This is actually a problem we rectified recently with GRB afterglows. You notice that we have the wideband sometimes far above the other filter bands. This is because of something called spectral indexing. So the range of values that we got in U, G, R, I, Z, and Y were not done with the same filters that are actually in Rubin. And there is a correlation between each filter when it evolves. So when we randomly uniformly distribute these values, we're not really correlating them between filters the way we should. And so we use something, we apply spectral indexing in order to compensate for that. So really, they should be in a much nicer format, looking something like this. Whereas you see they're kind of one under the other. And because this is from GRB Afterglows, this is a GRB Afterglows template. And so we have applied spectral indexing here correctly. That's why we're seeing a slight, discrepancy with the kilonova light curves here because we haven't applied spectral indexing, and that would be a whole other like 2 or 3 sections to kind of discuss. So left that out.
This is kind of nice because it graphs them out.
Yeah, it gets the job done.
Visually, it's very visual.
Gets the job done. Okay, so going to move on to the next section. And so we've created our instruments, we've created our Rubin Observatory, hypothetically. We've created our sky, we've created our universe, we've put things into that universe. And now we're going to take a step back. So now we're going to start adding the human perspective. How do we understand the level of efficiency, or how much can we trust Rubin to actually detect what it's detecting? Right, so this is where detection and characterization criteria come in. And so we define these filtering rules that help distinguish kilonova from other fast transients based on their light curve behavior. And there are 4 main filters that we use. So we have what signal to noise ratio we require for detection, how many detections we need to have of one transient in a specific filter, how rapidly the transient rises to its peak magnitude, and how rapidly the transient fades after reaching its peak magnitude. And so a kilonova is considered detected if it meets the following criteria. So often set to 1 to 2 detections above a certain signal to noise ratio, and that's at 3, 4, 5 sigma. We have filter requirements, so the detection must occur in in specific bands in order to count. So we know that kilonova rise in the blue and they fade in the red and high. They fade slower in the red and the near infrared. So we're more likely to capture them in those filters. And then we have time window consistency. So observations must occur within a plausible temporal window for a transient. Because if we capture it here, and then 3 days later, 3 weeks later, we're capturing it over there, the likelihood that it's the same detection is low because kilonova don't last that long. So these criteria are grounded in real survey cadence limitations and the nature of kilonova evolution. So fast rise, fast fade, strong wavelength dependence. And so we evaluated the light curve, it's detected the light curve, it's detected these events that we put in the sky. But how much of those detections, how much of those events has Rubin actually seen? And that's where characterization criteria comes in, we're going beyond detection. And so detecting a transient isn't enough, we want to understand what it is. For kilonova, characterization involves capturing parts of the light curve that help distinguish it from other transients, like its evolution. So for this demo, we define characterization as a rise rate, 0.3 magnitudes per day, and a fade rate, 0.1 magnitude, or this is wrong, 1 magnitude per day.
Which I might need to change some of those too, that was.
You check. Yeah. I think we can also change, I changed the thresholds to who wasn't detecting it, probably because of the likelihood not being very diverse. So we might need to change it from 3 back to 5, we can do that. So, I mentioned signal to noise ratio, I mentioned this 5 sigma rating, and the signal to noise ratio is a fundamental concept in observational astronomy for those of us who aren't astrophysicists. It quantifies how confidently we can say an observed signal or a transient event like a kilonova stands out against the background noise. And so Rubin has its own SNR function, but importing Rubin stuff in here would have been a nightmare, so I made my own. So now what you guys are gonna do is you're gonna take these custom detection, these detection criteria and these characterization criteria, and you're gonna create detection and characterization functions. So your goal is to define a function that takes a synthetic light curve and determines whether it satisfies the constraints you've set. So your function should check that the light curve has at least an n number of detections above this SNR threshold. Confirm that at least one detection is in each selected filter. Optionally, you can verify that the rise and fade rates fall within your defined range, but then you're really constricting your detected. This is why we have a 2-step process. We have it goes to the detected. Have we seen the light curve in above the SNR threshold? Have we seen it in 1 or 2 filters? And then it stops there because we're checking to see if the light curve matches these limits. And then we have a collection of light curves that we're detecting. Once we have that number, so let's say we've populated 3,000 of them. All right, 500 are detected by Rubin. How many of those is Rubin able to capture enough of this light curve to say, yes, this is a kilonova? And so here, we're going to use the following criteria to create 2 separate functions. And so in 2019 and 2022, Igor Andrioni and then me in 2025, yay, did an evaluation of these metrics based on general detections, 2 detection any filter separated by 15 minutes. And then we also had a much more stringent criteria, which was 2 detection in any filter separated by greater than 15 minutes. And we're seeing a rise rate of 0.3 magnitude per day and a fade rate of 1 magnitude per day. I think about that.
Those are backwards.
Yeah. What happens when you're writing it?
Yeah, so if you look at the light curves that we plotted before, you can see that the rise is quite steep.
Yeah.
And then the fade is like kind of steep.
Yeah.
So that's our visual demonstration of why we require that the rise rate is greater than 1 magnitude per day. And the fade rate is greater than 0.3 magnitudes per day.
Yeah, I was writing this the other night, I got them switched up, my bad. This is why sleep matters. All right, so I fixed those here, so just make sure that it's rise rate of 1 magnitude per day, because we're looking for this really sharp incline here. They rise really fast. And they fade really slow, so the slope needs to be slow.
We're doing 0.3, so fairly fast.
Yeah, but it's not faster than 1, so.
Yeah, I just need. Yeah.
That's true. Yes, that's why we call this a fast transient.
And this is why detection and characterization metrics being a series of steps and not just one detection metric is so important. Because then we're filtering out. You know, if another transient looks similar to this, are we actually seeing a kilonova, or are we seeing something else? And so Igor's and my original paper did detection criteria, this multi-detect as one detection metric, and then did the ZTF rest, which is the more stringent criteria, as something else. However, in the metrics that I'm writing for both GRB afterglows and rewriting for kilonova, it creates this two-step process. So we have the population, it goes through detection, so this general multi-detect, and then that collection of detected metrics, which is pretty general, it's just the light curves, then goes into the characterization. Are we seeing this really fast rise rate and slow, relatively slow fade rate? And so what I want you guys to do here is now use the information that I've given you, make sure that it's corrected for this rise rate and the fade rate, my bad, and write your functions. These are a little bit more technical. You're gonna have to be a little bit more creative. The solutions are there, and I have given you guys hints of what the code looks like.
What are the values we want for rise rate and fade rate? Okay.
I put them in day
Rise
1.
1, day 0.3,
Okay.
and then Shar put them in SLAT. And then I will push the the fully corrected filter demo to GitHub right afterwards.
Sure to get to the next sections, at least to talk through them. So if you haven't finished your characterization criteria, go ahead and just copy that from the solution. And then we can answer more questions if you want to go back and work on it later. But for now.
So these informed constraints sharpen classification accuracy. Helps us reduce like the number of false positives and help align filter logic with the physical models that we've built. SNR greater than 5 is widely, SNR equal to 5 is widely used in astronomy. And it's a really, really high false positive rate, so like 99% guaranteed, basically, high as you can go. When using simulated light curves in controlled metrics environment, because we can't, exactly replicate Rubin, we have lowered 3 sigma, and so you can test, as in the next step, in the next section, you can change how you iterate through the detection and characterization criteria. So it's to go ahead and start off at 5. If you see, hey, I'm not getting anything, lower to 3. And this is a really good way to kind of understand how this works and how we proceed when we're not detecting anything. So section 5, which we're starting now, is the section where we simulate a population of kilonova events by placing them across the sky and assigning each one a light curve. So now we're giving them a distance. We're giving them a place in the universe. So this allows us to later evaluate how many would be detectable by any given survey cadence. So typically when we generate a population, we'll use a volumetric event to estimate, we'll use a volumetric event rate to estimate how many events would occur in space and time. It's usually with a rate density of like something e to like the 8 megaparsecs cubed per year. So 1 over megaparsecs cubed per year. But usually generating that takes 15-20 minutes. And so we're going to hard code a number of kilonova just for you guys to see how these metrics work. So I want you guys to run this cell. And so we're gonna open the masked cadence that you guys did earlier. So this is the one that's gonna have the ecliptic, the galactic, and the visits masked. And this function here is inject uniform heel picks. This is going to uniformly distribute the population across the sphere at our position in the sky. Right? So it's gonna randomly inject uniformly across the sky. And then remember that these events are gonna be at different distances, and we have distance bound set pretty low at 30 to 250 right now. But generally, when we're estimating, kilonova efficiency with Rubin, we have them between 10 and 1200. And so for this section, what I want you guys to do is compute the extinction using SFD, randomly sample distance in megaparsec between 30 and 250, compute the distance modulus. So now we're going to be bringing those absolute magnitudes, we're going to make the parent magnitudes, and we're going to randomly sample a peak time between MJD range, start and finish. And so everything else is written for you. Go ahead and take a look at the solutions, try and say, hey, this is how you would start, and then go from there. So we have the population done. So we haven't plotted anything yet. We've just written the functions for detection, for characterization, and then to generate the light curves. To generate the population with the light curves. And so this is where everything we've set up. So light curves, extinction, survey depth, observation times have all started to come together. And so by putting these pieces into a single population generator, we're getting ready to test our detection and characterization logic in a way that actually reflects what Rubin would see on the sky. So even though we haven't run the generator yet, the way we define the K&E population metric is really important, especially in a technical manner. It encodes our assumptions about what kilonova look like and how they interact with Rubin's observation patterns. So the structure also lets us swap in different cadence files, change physical parameters, update detection thresholds without rewriting the entire pipeline. And then even to expand beyond this and what we do for all the metrics we're writing, a lot of this is very much standardized. And so this is where we move from theory, from modeling into simulation. We're no longer describing what kilonova might do, we're programming what they would do in the sky and letting Rubin observe them. So basically saying, Rubin, have at it.
Yeah, who can tell me one parameter that's included in your kilonova model? There are a lot of them, so more than one person can answer this.
I'm gonna start calling out people like we're in third grade. So don't make eye contact.
Oh, I'm just putting it online, so yeah. You might have to call people.
Okay. So what parameter, including your kilonova model?
Brightness,
Yeah,
Okay.
peak magnitude,
Mhm.
that is an important parameter.
So give me another one. Well, how about your programming partner?
so brightness and bandwidth,
So bandwidth is just for the filters, but which
Right.
filter it's detected in is important.
right?
So why do you think
Time frame of the,
very good.
the arm takes to rise and then fall.
Yeah.
Those are two different parameters.
Yeah,
Is right ascension and declination part of it too?
it's coordinates where it is in the sky.
So why are each of them necessary in order to determine, whether the kilonova is detected or not?
This is very strict parameters that define what is a kilonova.
That's true, the RA and DEC aren't necessarily,
That's just reference, that's housekeeping.
it does,
But what does it tell us
it's
about Rubin?
necessary to know whether or not we can find it though, right?
Mhm.
Say that again,
It's not, the RA and the DEC are necessary for us to know whether we'll find it with our sky survey.
what,
not because it's gonna change what the kilonova looks like, but because if we never look at that RA index, then we definitely won't find it.
And also, if it's in a place where Rubin doesn't look for a long time or look at very well, the depth or the understanding that we're gonna get of that kilonova, of that single event, may not be as good as one where it's in a really high number visit place.
Yeah, so if you recall the sky maps we made at the beginning where some pieces of the sky were a little bluer and some of them were a little greener. It could matter whether we're in a bluer or greener part of the sky, whether we actually see this kilonova.
Well, heaven forbid, what if we discovered a kilonova inside the Milky Way
Oh, we'd be
galaxy?
out.
That one would be pretty bright. That one would be pretty hard to miss.
The gamma ray, that's
Pretty
what we're
great.
really worried about.
We,
Oh, that could be a life extinction event for
If it's-
somebody in
it's
the
possible.
galaxy.
Yeah,
Or whatever galaxy it occurs,
yeah.
can sterilize a bubble within 10, like 2 or 3 parsecs.
We're not wrong.
All right, let's move on.
All right. So no more coding for you guys. So sorry to give you guys so much in class work. But now we're gonna be applying population injection and test the recovery. So everything that we've done, we're gonna generate the population. It all has been folded into it. We're gonna run the population generator. And that's gonna download metadata and the population for the kilonova in this cell here. And so this is the point where simulated kilonova and are dropped across the sky, tested against Rubin's observation cadence, filter by filter, epoch by epoch. And so the logic here mirrors how real-time transient pipelines work. So we inject events. Each event is assigned a light curve and injected into a realistic observing field using the uniform sky distribution. We have the first pass of detection. So we check if Rubin would have caught the event based on signal to noise, cadence sampling, filter coverage. And so this step filters out events that wouldn't make it past an alert threshold in a live survey. And then we have the second pass, which is characterization. So for the events that were detected, we assess whether the light curve has enough information to distinguish the source as kilonova light. That means checking for the rise and fade behavior, the time coverage, and the multi-filter, detection. So conditions needed to extract physical insights. So by doing it this way, we avoid spending resources analyzing events Rubin didn't really observe. So when we do apply this to Rubin, and this means that with alerts going out, with information going out, so people can say, hey, Rubin actually did see this. There is some confidence here. We can now use resources outside of Rubin to observe. So now we're going to run this cell here. So this is plotting everything.
This should work just as is for everyone.
Yeah, we're not programming anything. Not to rerun.
Mhm.
Changes. Okay.
So our goal output is just like we made the maps of the cadence at the beginning of this notebook, we're now gonna map where we've injected and where we've retrieved all of these kilonova that we've modeled with our beautiful, beautiful light curves.
So this is set to 2,000 events. It's going to take a few minutes to run.
All right.
So we can discuss the things in the meantime.
Yeah. Do you want to give a sneak peek of section 7?
I haven't tried to. I guess we can do what you've done to wait, never mind. Minor.
Nice.
All right, so we have 2,000 kilonova events that are placed in the sky. 150 were detected by Rubin, and 2 were characterized over 10 years. So we're doing better than we're doing now. All right, and so we have a uniform sky distribution of events, of the injected events. So this is that purple here, and that yellow is going to be the detected numbers. So we've populated a series, distributed across the sky, 2,000 of them, and then detected them in the yellow here. Why do we not have any detected above 0?
Like in the top half.
Yeah.
Let's see that.
Bingo, there we go. Alright, so why did we not just plot 2,000 in the southern hemisphere? Well, there's a whole other universe in the northern hemisphere. And so we created an even distribution across the universe. So that's where this, mimicking it. So we're not biasing the universe towards Rubin. Rubin has to look towards the universe. Right? That's detection. And then we have these 2 little dots characterization. We're really proud of those 2 little dots. Be very proud of your 2 little dots. All right, that means that you have seen it completely enough to say, we detected 2 kilonova in, both in the rise and the fade, we've gotten it.
So some may say that the Rubin Observatory's legacy survey of space and time is not well designed to find kilonova. They would be correct, but however, it is happening, so at least we'll see what we can do with it.
And for as many kilonova as Rubin is estimated to detect, so in the 50s over 10 years, the GRB afterglow numbers are much better than that. So we may not detect the kilonova, but the likelihood that we get an afterglow from it is higher. And this is multi-messenger astronomy for a reason.
And I think that's a good plug for tomorrow, because, with the boom filtering stuff, the idea is to combine Rubin with some of these other surveys
Yes,
to
yeah.
increase the cadence. So I think that's a good, tomorrow we'll talk a bit about some of this joint filtering and, that kind of.
Totally.
And so these helix maps show detection and characterization efficiency across the sky. Areas with higher values are where Rubin's cadence aligns well with our transient models, and this gives us really good efficiency recovery. The gaps in low efficiency regions often trace the limits of the LSST footprint, or areas with fewer irrelevant filters, which means lesser detections. Right, and this is why you can kind of start to see here that in where the ecliptic spur is and the galactic plane on either sides, you notice there's not as many detected events here. So we're really seeing how Rubin is looking at this area and why it's important to really focus on, those strong kilonova units. All right. So I'm sitting really late at night in my office or at home in my basement, trying to ignore the world and get these metrics out. And I do a really good job of producing all of these light curve plots and getting them to output something. But how do we know that in 3D or in real time, all right, it's effective? How do we diagnose if what is being programmed is doing so confidently, correctly? And so, yeah, the code might work, 1 + 1 = 2, but if you haven't given context to that, it's just a value. And so between Federica and Shar, who've worked alongside me, they have really helped to help diagnose, some maybe intrinsic issues, like why were we seeing some of these light curves in different photometric filters above the other when they shouldn't be. Right? And so you can want to talk about the diagnostic plots and their significance.
Yeah, whenever you code something, you should plot as many things as possible. And you should have an idea of what that plot should look like. So here, for instance, we have our right ascension and declination, which are like your sky coordinates. So can you just be stationary on some plots?
Yeah.
So we know, for instance, why do we have recovered events over all RAs index? Because we're not supposed to find any in the north.
Mm-hmm.
So we know, for instance, that we shouldn't be finding any,
It wasn't like that before.
Well, it's just, but you just have to look at the axes. It only goes up to 0.2.
You're so
So it's
right.
fine, yeah.
All right. So if you look at this, the axis for this declination here, you shouldn't be seeing very far on the positive side because that means you're looking in the northern sky and we don't see anything there, so that's good. We do see events at a like uniform-ish, random-ish distribution on our other parameters, which is good, and we can see that the magnitude is plotted on the y-axis, so brighter is higher on these plots, and things that are brighter are more detected, and those things that are fairly dim are not detected. So far, things are looking good. We don't need to talk about these ones. The issue we issue we had for peak times is not an issue that you all will have. But for a long time, we had nothing detected in year 1 or year 2. It turns out that's because the LSST has been planned to start for a long time. Like it originally was gonna start, I don't even remember, like 2020 or something. So we were using an old date for when our kilonova started to exist in the sky, and then we didn't find any because now the current version of the survey simulation starts in 2025. And I was like, well, no kidding, you didn't find anything in 2023. That's because the survey hasn't started yet. So just plot everything.
It took what, a researcher, someone who got a PhD and a PhD student, how many months?
Several months.
To figure that out.
We did have this book for several months. Yeah, that's okay.
So this kind of shows us, hey, is there any discrepancies? How is the cadence? How is the simulation, our metrics working? Specifically, the metrics we designed working each year. Is it doing so correctly? And so this really shows that the iterative component of this metric of these codes, all right, is working properly.
If you had a bigger y-axis here, you'd probably be concerned that year 9 has like half as many detections as all the rest of the years. However, the actual numbers on the y-axis are pretty low, so this is within like a normal random variation. Stochastic, blah, blah, blah. Yeah, we already showed deck, so yeah. And now you guys know how to build a metric to assess whether a survey cadence can find a specific kind of transient. Good job, everyone.
Yay.
And so Rubin, so now here are some examples of what the GRB afterglows metric that we've finished working on really looks like. So Rubin is able to see a little bit higher above the equator than we programmed in our demo. And we figured out how to, we sampled from Chenko, that's the name?
Yes.
From the catalog that he made of GRB afterglows, or they made from GRB afterglows. And we were able to create a spectral indexing, so this is evenly correlated. And then over 10 years, between 2 different cadences, one that does 3 visits within a night and one that does 4 visits within a night, we're able to see that over 10 years, we're detecting 148, 139 GRB afterglows, and then we're able to characterize it, obviously with different criteria. And so that's about 10 a year. That's not bad.
GRB afterglows are not as rare as kilonova, but still pretty hard to find because anything that evolves this rapidly, like if you don't look within a week, you've lost it forever. So pretty exciting to find a lot of those.
All right, thank you.
All right, folks, thanks for a good day 1. We'll start around 9 tomorrow morning, talking about ZTF filtering and such. So we'll kind of continue on this topic, and otherwise, see y'all tomorrow. Bye, guys.